Hey everyone, this is 2024 free response question number 3. I'm going to do this one first. I like this one better than question 2 and kind of slow to putting these videos up because of adulting and doing things. But it talks about sterling silver. So it's an alloy commonly used to make jewelry, 92.5% silver and other 7.5% other metals like copper by mass. Over time, Ag2S can form when it reacts with hydrogen sulfide, represented by this equation here. Okay, so we have Ag2S. First question, oxidation numbers. So this one, you just got to know some of these things, some of the rules for oxidation numbers, but if it's by itself, oxidation number is 0. If it's as a compound, the oxidation number is just the charge of that. So sulfide you can get from the periodic table, and that's because it's in the 6th column. It is -2. So Ag is going to be +1 to balance that out. So Ag has a +1 oxidation number. So this is probably 1 point. Following table contains atomic radii of silver and copper, 165, 145. So why can sterling silver better be classified as a substitutional alloy versus an interstitial alloy? So I don't know exactly how they want this question to be answered, but I think of interstitial alloy is something that has smaller atoms like carbon, much smaller than this size comparison. So you're talking, if you have silver, this is silver atoms, and interstitial means it's going to fit into these interstices of the silver atoms. So that means you're talking about, this is 165 picometers for that radius. This is probably going to be like 20 or something, I don't know, some dramatic difference. And so you want something that's much smaller. Copper is relatively the same size. It's not that much smaller. Maybe just like, 145 compared to 165 is not, that radius is not much difference. So because these are so similar in size, you're going to talk about, silver being like this, copper being like this, and that size difference is not going to be that much different. And so I just wrote down silver and copper are fairly close in atomic radius. So copper atoms replacing silver atoms would not result in an alloy that had tiny atoms stabilizing the metal, the silver metal atoms, and that would be an interstitial alloy. So I don't know. I just gave my best shot at this answer. Not sure how they want it answered, but I'm sure that's 1 point. No guarantees, of course, on any of these. This is just my interpretation of the question. Using principles of atomic structure in Coulomb's law, why does silver have a larger atomic radius than copper does? Let me get a periodic table for this one. Hang on a second. Okay, so if you look at the periodic table, this is silver right here. It's in the 5th row, which is the 4D sub-level. Okay, so remember, it goes 1, n equals 2, n equals 3, n equals 4, but this is 3D, right? So this copper is in the 3D block, silver is 4D block. So why does copper have a smaller atomic radius in Coulomb's law? So you want to talk about, anytime you have Coulomb's law, you want to talk about attractions between charges, and so I just wrote silver has valence electrons in the 4D energy level, whereas copper has it's in the 3D level. 4D level is farther from the nucleus. Okay, so if it's farther from the nucleus, less Coulombic attractive forces from the positive nucleus resulting in a larger radius. Coulomb's law is you have Q1, Q2 over R squared, right? This is the attraction. And this charge these two charges here, well, the charges are going to be, the positive and negative charges, but this distance here, right? So if it's farther away, which means that the 4D level compared to the 3D level, then the 4D is a bigger radius. Bigger radius is going to mean that this overall thing becomes smaller because it's in the denominator, and the attraction therefore drops. So make sure you write about attractions when it talks about Coulomb's law. Don't just write about the 4D level versus 3D level is farther away. I don't think that's going to be good enough. Okay, next part. The Ag2S tarnish on the sterling silver can be removed until only sterling silver remains. Student weighing the tarnish both before and after removing Ag2S records the data. So this is the data before tarnishing, after tarnish, removed. Calculate the moles of silver, just silver atoms. Okay, so this is the key thing here. Removed. Assuming only Ag2. So we have to subtract these two things here. We have mass before and mass after. We got to subtract those two numbers. So we get that mass, which is 10.27 grams. And then we're going to take that, convert to moles of Ag2S. So I change that. You give me the molar mass, so 247.8 moles. But then there's a mole ratio of 2 to 1 from 1 mole of Ag2S to 2 moles of Ag, and that gives me 0.0829 moles of silver. So that's probably maybe 2 points. Not sure about that one. Okay. Rhodium is placed on a plating process used to protect its sterling silver from tarnishing, as well as electroplating, depositing solid rhodium on the metal from an acidified solution of rhodium. Okay, half reactions. Now we're talking electrochemistry here. So give me some half reactions of this. So, first question, write a balanced equation for plating rhodium from acidified solution. Yeah, so this one here, you gotta know that we're plating solid rhodium. That means we are keeping, so this reaction here, we're gonna keep because we're plating this solid rhodium here. So we gotta keep that as a product, right? So we need this as a product. That means if this one we're keeping as reduction, this one we're gonna flip. So this is gonna flip, that's gonna become oxidation. And then to balance it, because this has 3 electrons here and this has 4 electrons, we need to make the electrons even out. So this reaction, we're gonna have to multiply this by 4. And this one we're gonna have to multiply by 3 so that we have 12 electrons switching places, and that'll give us a balanced reaction. So if I did that, go ahead, take this one times 4 times 3. This is flipped, and I got 4 RH3 plus, and this is 6 waters. So 3 times 2 is 6, and that's going to give me 4 rhodium solid, and then the 12 H pluses on the right side. Remember, this is all flipped around. Plus, oops, I forgot my oxygen. 3O2. Okay, so 4 RH3 plus, and then 6. Let's just keep this straight, right? So this here, and then for this 12. Yeah, that's right. Okay. Next, E cell. Calculate E cell. So when you multiply, remember you do not multiply the E naught at all because the potential does not change. That's only for thermo. If you have delta H, you would change that, but E naught does not change. So plus 0.80, and then plus negative 1.23, and I got negative 0.43. Okay, next. Okay, so next part, based on your answer, why does the process require an external power source? Well, okay, so they didn't even ask you if you thought it was favorable or not. They just said, they're just telling you, why does it need a power source? Which means it has to not be favorable, right? So remember, there's this equation on the equation sheet. Delta G equals negative NFE. If delta G is negative, that means E naught is positive, and then that's favorable. If delta G is negative, the reaction is favorable. If it's not negative, which is, if it's positive, that means this reaction is not favorable. It's not going to go by itself. That means you have to have something to drive the reaction. And so that tells me that E is negative, which is what we got. We got a negative value for E naught. So I just wrote, since E cell is negative 0.43, delta G is positive, right? So this equation here, negative NFE, delta G would be positive. If that's positive, it's not thermodynamically favorable, and we need a power source to run it. So, and then the last part here, I think this is the last part, calculate the length and time requires to plate 2.8 grams of rhodium on a piece of sterling silver if 2 coulombs per second of current is applied. I call this a super bonus part because in my class, we never get to even calculate. We don't have time to learn this. But if you know how to convert units, you can pretty much solve it just by knowing the units of stuff. Okay, so a couple things here. This is, and anytime I see grams, I'm gonna change this to moles. So I'm gonna change that to moles, and that gives me 0.0272 moles of rhodium. Okay, so once you know you're at 0.272 moles of rhodium, O272, rhodium, how does that connect to electrons? And we know from our previous part here, rhodium, 1 mole of rhodium, I need 3 moles of electrons. Because for every mole of rhodium, I need 3 moles of electrons. And I also know Faraday's constant tells me that I have 96485 coulombs per mole of electrons. Okay, so what I did was, if I know that I have this thing here, 0.0272 moles of rhodium, and for every mole of rhodium, I have 3 moles of electrons. For every mole of electrons requires 96485 coulombs. So this is all just unit conversion, right? If you know how to convert units, I tell people if you are good with units, you can solve a lot of stuff on the AP Chem test. Then that gives me 7873 coulombs that I need. And if I have a current of 2 coulombs per second, well, 2 coulombs per second is going to give me, so basically cut that in half, 3936.6 seconds, or 3940 seconds. So that's, I think, how you solve that problem. Okay.